Hi everyone. So previous class we have discussed about time varying electromagnetic fields, time varying Maxwell's equations, time varying integral form and differential form Maxwell equations. In this class we are going to discuss about summarize time varying field Maxwell's time varying integral form and differential form Maxwell's equations, time invariant integral form and differential form Maxwell's equations, and also discuss about Maxwell's equations for free space, and also discuss about Maxwell's equations for free space. First, we are going to summarize time varying field Maxwell's equations. So these equations, these expressions already discussed in previous class clearly. Now here summarization. So differential form, Faraday's law. So what is the integral form of the Faraday's law? Integral form of Faraday's law, Maxwell equation, closed line integral of E bar dot dl bar is equal minus open surface integral of dou v bar by dou t dot ds bar. And what is the differential form of the Faraday's law, Maxwell equation? Del cross E bar is equal minus dou v bar by dou t. So these equations already clearly explained and already clearly derived in previous classes. And the second Maxwell equation is Ampere's circuital law. So what is the integral form of the Ampere's circuital law? Closed line integral of h bar dot dl bar is equal open surface integral of j bar plus dou t bar by dou t dot ds bar. So that is the integral form of the Ampere circuital law. That is second Maxwell equation integral form. And differential form of Ampere circuital law. Del cross h bar is equal j bar plus dou t bar by dou t. So this is the differential form or point form of the Ampere circuital law. In this differential form, on RHS side, the RHS term is the combination of two current densities, that are conduction current density and displacement current densities. And third Maxwell equation is Gauss law for electric fields. So what is the Gauss law for electric field? Integral form of the Maxwell equation. Closed surface integral of d bar dot ds bar is equal to q, that is equal open volume integral of rho v into dv. So that is the integral form of the Maxwell equation, Gauss law for electric field. And differential form, del dot d bar is equal to rho v. Del dot d bar is equal to rho v. And fourth Maxwell equation is Gauss law for magnetic fields. And what is the integral form of the Gauss law for magnetic field Maxwell equation? Closed surface integral of b bar dot ds bar is equal to 0, and its differential form or point form is del dot b bar is equal to 0. So this is the summarization of time varying field Maxwell's equations. So keep in mind these equations. Keep in mind these expressions. Maxwell's equations are very important expression. Integral form and differential of Maxwell's equations are very important. Keep in mind all formulas, all Maxwell's equations. Next, summarization of time varying, time invariant Maxwell's equations or static Maxwell's equation. So time invariant or static Maxwell's equations already discussed in electrostatic and magnetostatic concepts. And what are the previous Maxwell's equations? That are time varying Maxwell's equations. Time invariant means in the above equation, dou v bar by dou t, the magnetic flux density is varying with respect to time. And dou d bar by dou t, electric flux density is varying with respect to time. If the magnetic flux density and electric flux density is not varying with respect to time, so not varying with respect to time means that is time invariant or static fields. So that is for static fields or time invariant fields, dou v bar by dou t is 0 and dou d bar by dou t is 0. So in this equation, substitute dou v bar by dou t is equal to 0 and dou d bar by dou t is equal to 0, we get time invariant integral form and differential form Maxwell's equations. So these are the Maxwell's equations of time varying fields. How to find out time invariant or static Maxwell's equations? In these equations, magnetic flux density not varying with respect to time, that is dou v bar by dou t is equal to 0, we get time invariant Maxwell's equations. And magnetic electric flux density is not varying with respect to time, that is dou d bar by dou t is equal to 0. Substitute dou d bar by dou t is equal to 0, we get time invariant Maxwell's equations. So see the table, time invariant or static Maxwell's equations, integral form and differential form. Closed line integral of E bar dot dl bar is equal to 0. That is the statement of conservative nature of the field. Conservative nature of the field. The electric field intensity, the electric field intensity around any closed path in a static electric field must be 0. That is significance of conservative nature of the field. And differential form, del cross E bar is equal to 0. And the second Maxwell equation for time invariant case, closed line integral of h bar dot dl bar is equal to I, and differential form is del cross h bar is equal to j bar. And third Maxwell equation is for time invariant Gauss law for electric fields, that is closed surface integral of d bar dot ds bar is equal to q. Here there is no derivative part. So because of that, this equation is as it is same. And differential form is del dot d bar is equal to rho v. And fourth Maxwell equation, closed surface integral of b bar dot ds bar is equal to 0. And differential form del dot d bar is equal to 0. So these are the Maxwell equations for time invariant or static field Maxwell's equations. Next, we are going to discuss about Maxwell's equations for free space. Maxwell's equations for free space. For free space, there is no conductivity of the material, and there is no volume charge density, and there is no conduction current density. So let us consider the medium is free space. For free space, the permittivity epsilon is equal to epsilon naught and permeability mu is equal to mu naught. So what is the conditions of the free space? There is no conductivity of the material. There is no conductivity of the material means sigma is equal to 0. So what is the conduction current density? Jc bar is equal to sigma into E bar. If there is no conduction current, if there is no conductivity of the material, then the conduction current density is also 0. And the volume charge density rho is equal to 0. So these are the conditions of the free space. Applying these conditions, free space conditions, into time varying field Maxwell's equations. What are the time varying field Maxwell's equations? These are the time varying field Maxwell's equations. In this tabular column, we can apply free space conditions. What are the free space conditions? Volume charge density rho is equal to 0. Conduction current density Jc bar is equal to 0, and conductivity of the material sigma is equal to 0. Substitute these conditions into in this tabular column, we get Maxwell's equations for free space. So what is the first Maxwell equation? Integral form and differential form. Differential form del cross E bar is equal to dou v bar by dou t minus dou v bar by dou t, and integral form closed line integral of E bar dot dl bar is equal minus open surface integral of dou v bar by dou t dot ds bar. And second Maxwell equation, differential form del cross h bar is equal dou d bar by dou t, and integral form closed line integral of h bar dot dl bar is equal open surface integral of dou d bar by dou t dot ds bar. And third Maxwell equation, what is the for time varying field? Third Maxwell equation, differential form del dot d bar is equal to rho v. For free space, there is no volume charge density. Rho v is equal to 0. So what is the resultant Maxwell equation in free space? Del dot d bar is equal to 0. And integral form Integral form, closed surface integral of d bar dot ds bar is equal to 0. The fourth one is same, as it is same. Del dot b bar is equal to 0, and integral form, closed surface integral of b bar dot ds bar is equal to 0. So these are the Maxwell's equations for free space. Next, Maxwell's equations for good conductor. So what is the conditions of the good conductor? For the good conductor, volume charge density rho is 0 and the conduction current density is very much greater than the displacement current density. So conduction current density Jc is very much greater than displacement current density and the volume charge density rho is 0. Applying these conditions into time varying field Maxwell's equations, we get Maxwell equations for good conductors. First expression as it is same, and second expression. So what is the time varying field Maxwell equation? Second expression, del cross h bar is equal to j bar plus dou d bar by dou t. What is the first term? Conduction current density. What is the second term? Displacement current density. For the good conductor, what is the conduction? What is the condition? Conduction current density is more than the displacement current density. So compared to the conduction current density, displacement current density is very less. So because of that, neglecting displacement current density value. So we have the resultant expression is del cross h bar is equal to j bar and the integral form. Closed line integral of h bar dot dl bar is equal open surface integral of j bar dot ds bar. And third equation. For the good conductor, there is no volume charge density. Rho is equal to 0. Applying that condition here, del dot d bar is equal to 0. And integral form, closed surface integral of d bar dot ds bar is equal to 0. And fourth equation as it is same. Fourth expression as it is same. So these are the Maxwell's equations for good conductor.